So the next thing to discuss here is the different operations we can perform on matrices. So here we're going to discuss how we can modify a matrix without changing its true properties. We can add one row to another without changing things. This is what we would have done when performing simplifications of systems of linear equations. We can swap rows in a matrix, but do remember that this always multiplies the determinant by -1. We can multiply a row by a scalar, and this doesn't affect the relationship between the different numbers in that row. Here's a matrix below. This is the identity matrix. So we can add row 1 to row 2. This gives 1, 0, 1, 1. We could, for example, multiply row 1 by 2. This gives us 2, 0, 0, 1. And we can also swap rows. And doing that, we're going to get 0, 1, 1, 0. This doesn't essentially affect the properties of this matrix. So why do we do this? We do this so that we can get this matrix into what's called reduced row echelon form. We'll discuss that later. We can add and multiply matrices. So adding matrices is very much the same as adding x, y, z components in algebra. You're simply adding a11 with b11, a12 with b12, a21 with b21, and a22 with b22, summing them over here. Subtraction works the very same way. With multiplication of matrices, what we need to know is that we can't simply add any type of matrix with another type of matrix. Of course, the same does apply for addition. But we must have a situation where if we're multiplying a matrix that is of size n by n with another matrix that's of size h by k, we have to have n equals h. We can multiply a 1 by 2 matrix with a 2 by 1 matrix, for example, but we can't multiply a 1 by 2 matrix by a 1 by 2 matrix. That can't happen. The two numbers in here in the middle must always be the same. So here is another example. We've got a 3 by 2 matrix by a 2 by 3 matrix. The 2's essentially disappear and we get a 3 by 3 sized product. Again here, a 4 by 2 matrix multiplied by a 2 by 3 gives a 4 by 3 product. But, of course, remember that a 2 by 3 by a 4 by 2 matrix will be undefined. So, of course, the order does matter. Let's take a vector, xy, and multiply that by 1, 2. So to do that, we're going to multiply a11 by b11. We're going to get x down here. We're then going to multiply a11 by b12. That's going to give us 2x. We're then going to multiply a21 by b21 is going to give us y times 1. It's going to give us y down here. a21 multiplied by b12 is going to give us 2 times y, which is 2y down here. Now an example of a 3 by 3 matrix, we can get the matrix 1, 1, 1, 1, 3, 1, 1, 4, 16. And we're going to multiply this by x, y, z. So to do that, we're going to multiply row 1 by column 1. So that'll give us 1 times x, 1 times y, 1 times z. We get that down here. We're then going to multiply row 2 by column 1. We get 1 times x, 3 times y, 9 times z. And then we're finally going to multiply row 3 by column 1. 1 times x, 4 times y, 16 times z. Get this down below, and simplifying this down, this is our final matrix. Lastly, multiplying two matrices of the same size is slightly more complicated. So again, we're going to follow the exact same procedure. However, it works out a bit longer. We're going to have row 1 multiplied by column 1, row 1 by column 2, row 1 by column 3. That produces row 1 of our new matrix. So we're going to have 1 times A plus 1 times D plus 1 times G. That's going to be our first component of our first row in our new matrix. We're then going to have 1 times B, 1 times E, 1 times H. That's going to be the second component of the first row. So what we end up with is this down here. A plus D plus G from the first multiplication, B plus E plus H from the second multiplication, and C plus F plus K from the third. If you look here, we then move that down to row 2. We go row 2 by column 1. That gives us this here. So if you have a look at it, a matrix written like this, A11, A12, A13. The components match up with the row and column of the matrix product. You can use this to remember what part of each matrix goes where. So, getting a matrix to reduce row echelon form. This is known as Gauss-Jordan elimination.